Episode 4, Dynamic Programming. You now have the Bellman equations, the recipe for optimal behavior. But a recipe isn't a meal. How do you actually compute the value of every state? How do you find the optimal policy? This is where theory becomes algorithm. In this episode, we'll build 3 methods that solve MDPs when the model is known: policy evaluation, policy iteration, and value iteration. These are the first real algorithms of the course, the ones that turn beautiful equations into working code. And at the end, we'll discover a unifying principle, generalized policy iteration, that secretly underlies every algorithm in reinforcement learning. Let's recall where we are. In episode 3, we defined value functions. V_pi of S tells us the expected return from state S under policy pi. Q_pi of SA adds the action dimension. We derived the Bellman equation. The value of a state equals the immediate reward plus the discounted value of the next state. And we found the Bellman optimality equations for V* and Q*, which use a max instead of an average. The Bellman equations describe the relationships that the correct values must satisfy. But they don't tell us how to find those values. That's what dynamic programming does. It gives us iterative algorithms that compute values by repeatedly applying the Bellman equation until the answer converges. Our first algorithm is policy evaluation. Given a fixed policy PI, we want to compute V_pi for every state. The Bellman equation tells us the answer must satisfy this relationship. But how do we find it? The idea is beautifully simple. Start with any initial guess, say all zeros, and repeatedly apply the Bellman equation as an update rule. V_k+1 of S equals the sum over actions of pi of a given S times the sum over next states and rewards of the transition probability times the reward plus gamma times V_k of S prime. Each sweep through all states produces a better estimate. This works because the Bellman operator is a contraction. Applying it always brings you closer to the true answer. The distance shrinks by a factor of gamma with each sweep. Since gamma is less than 1, the estimates converge to V_pi. Let's watch this on our 4x4 grid. The terminal state is at position 0, 0. Every step costs -1. We're evaluating a random policy where the agent picks each direction with equal probability. At iteration 0, all values are 0. After one sweep, every non-terminal state drops to -1. That's just the immediate step cost. After 2 sweeps, states near the terminal start differentiating, -1.68 next to it, but -1.90 further away. By iteration 10, a clear gradient has formed. States close to the terminal have higher values because the random walk reaches the goal sooner. After convergence, the values settle. The farthest corner, state 3,3, reaches -9.36. Under a random policy, the agent wastes enormous time bouncing around. We stop when the maximum change across all states drops below a threshold theta. The stopping rule is max over all S of the absolute difference between Vk+1 and Vk is less than theta. Policy evaluation tells us how good the current policy is, but we want to make it better. That's where policy improvement comes in. The idea is, given V_pi, construct a new policy that acts greedily. For each state, compute Q_pi of SA, which is just the reward plus gamma times V_pi of the next state, and pick the action with the highest Q value. This new policy pi prime is guaranteed to be at least as good as pi. If it's strictly better anywhere, It's strictly better everywhere it differs. Now combine the two steps. Policy iteration alternates between full policy evaluation and greedy improvement. Evaluate the policy, improve it, evaluate again, improve again, until the policy stops changing. At that point, the greedy policy equals the current policy, which means the Bellman optimality equation is satisfied. You've found pi star. Let's trace this on our grid. We start with the random policy. After evaluating it, we get those slowly decaying values we just saw. Now we improve. For state 0, 1, the Q value for going left is -1, far better than up, down, or right. The greedy policy says go left. State 1, 0 says go up. Every state now points toward the terminal. After evaluating this new greedy policy, the values jump dramatically. State 3, 3 goes from -9.36 to -4.69. That's the power of following a good policy instead of a random one. We improve again. The policy barely changes, just some tie breaking on the diagonal. Evaluate once more. The values haven't changed. The policy is stable. We've found the optimal policy in just 3 iterations of the outer loop. 3 iterations. That's the remarkable efficiency of policy iteration. Even though each evaluation is expensive, requiring many sweeps to converge, the outer loop typically needs only a handful of cycles. Policy iteration works brilliantly, but there's a catch. Each evaluation step runs until convergence. For our small grid, that means many sweeps per iteration. Can we do better? Value iteration says yes. Instead of fully evaluating the policy before improving, do both simultaneously. The update rule combines the Bellman evaluation and the max operator. V sub k plus 1 of S equals the max over actions of the reward plus gamma times V sub k of S prime. One sweep, one update per state. No inner loop. Each iteration does a single pass through all states, taking the max over actions. Watch the grid again, but this time under value iteration. After sweep 1, all states hit -1. After sweep 2, states adjacent to the terminal stay at -1 because the max locks in the optimal action immediately. The values propagate outward from the terminal like a wave. After sweep 3, cells at Manhattan, distance 3, have their final values. By sweep 7, every cell has converged. Value iteration solved our grid in just 7 sweeps. Why 7? The farthest state is at Manhattan distance 6 from the terminal. Each sweep propagates the correct value one step further. 6 sweeps to reach every cell, plus 1 to confirm convergence. The max operator is the key. It immediately commits to the best action, rather than averaging over a random policy. After convergence, extract the optimal policy by computing argmax for each state. The result is the same optimal policy we found with policy iteration. Now step back and see the bigger picture. Policy iteration does full evaluation, then improvement. Value iteration does minimal evaluation with immediate improvement. These are 2 extremes of a spectrum. Generalized Policy Iteration, or GPI, is the idea that you can interleave evaluation and improvement at any granularity. Do 3 sweeps of evaluation, then improve, or evaluate one state and immediately improve. It all works. Think of evaluation and improvement as 2 forces. Evaluation makes the value function consistent with the current policy. Improvement makes the policy greedy with respect to the current value function. These forces pull in different directions, but they converge to the same fixed point, the optimal policy and the optimal value function. Here's the deep insight. Every reinforcement learning algorithm you will encounter in this course. Monte Carlo TD learning, Q-learning, policy gradients, even deep RL, is an instance of GPI. They all maintain a value estimate and a policy, and they improve both. The only difference is how they do the evaluation step. Let's consolidate with a focused walkthrough. Our 4x4 grid. Terminal at 0, 0. Step cost -1. Gamma 0.9. First, policy evaluation under the random policy. Watch the heat map evolve. Iteration 1, everything is -1. Iteration 3, a gradient appears near the terminal. Iteration 10, the landscape is clearly shaped. At convergence, state 01 is -5.76, state 33 is -9.36. Now, policy improvement. Compute Q values for each state. State 01 has Q left equals -1. That's the best action, because it leads directly to the terminal. The greedy policy says go left. State 11 has two equally good actions, up and left, because both lead to cells of equal value. Evaluate the improved policy. The values transform. State 33 jumps from -9.36 to -4.69. That's because the optimal policy takes exactly 6 steps from 33 to the terminal, with cumulative discounted cost of 4.69. Compare. The random policy's value at 33 is -9.36. The optimal policy's value is -4.69. A factor of 2 improvement, just by choosing the right directions. Here's the deeper truth of this episode. Dynamic programming is the only approach that requires a perfect model of the environment. You need to know every transition probability, every reward. In the real world, you almost never have this. So why study it? Because dynamic programming reveals the structure that all RL algorithms share. Policy evaluation shows how to assess a strategy. Policy improvement shows how to upgrade it. GPI shows that these two operations, interleaved in any way, converge to optimality. When we move to model-free methods in the next module, we'll be doing exactly the same thing. Evaluation and improvement, but estimating values from experience instead of computing them from a model. The GPI framework will stay with us for the entire course. It's the skeleton key. Let's lock in the essentials. First, policy evaluation computes VPI by iteratively applying the Bellman equation. Second, policy improvement constructs a greedy policy from VPI, guaranteed to be at least as good. Third, policy iteration alternates between these two steps and converges to pi star. Fourth, value iteration combines them into a single update with a max operator. And the unifying idea, generalized policy iteration. Evaluate, improve, repeat. Every RL algorithm follows this pattern. In the next episode, we leave the world of known models behind. What if you can't compute expectations over transitions? What if all you have is experience, sequences of states, actions, and rewards? Monte Carlo methods show you how to learn from complete episodes. See you there.